Okay, it's 8:20. So let's start with announcements. I mentioned on Monday that self-service had Physics 111C's time incorrect. That has now been corrected. So the time for 111C next semester is the exact same time block as 110C this semester. Monday, Wednesday, Friday, 8:20 to 9:10. Currently scheduled for this room. But if the number of daily attendance is 17 or less, I'm probably going to change the room to one over in the physics department. But just stay tuned for that, okay? For now, the important thing is the time has been changed to what we intended it to be, okay? Monday, Wednesday, Friday, 8:20 to 9:10, with a Thursday class that is all done online, just like this semester, just like this semester. And of course, there's a lab next semester too. And you have to choose a Monday section or a Tuesday section in the afternoon, just like this semester. Okay. Okay, so that's been corrected in self-service. And so for those of you who start registering tomorrow, that you can now have the course with the correct time. In terms of things to think about here, we have next homework set due tomorrow evening. I have decided I'm not going to do a quiz on Friday. Okay. You're currently working on your lab exam. Okay. Don't forget to finish that up and upload a single PDF document onto Blackboard that is your work for the exam. That's the lab for this week. Okay. And next week lab is back to its normal kind of operation. That is to say, we do a new experiment in the lab. Okay, that's next week. Another thing that's coming up next week on the syllabus for 110C is our third midterm, midterm 3. Now the syllabus has it scheduled for next Monday, but I'm going to move it to Wednesday. I don't like the idea of having the exam on the same day where there's a lab. Some people have Monday lab, you know, and that kind of puts them at a disadvantage to working on the midterm if they had to have to spend 3 hours in the afternoon in lab. So I'm going to move it to Wednesday, next Wednesday, midterm 3. The material, chapter 10, chapter 11, and the first 3 sections of chapter 15, which is what we're starting today. Okay. I have uploaded a practice exam like I did for the others. And I list that information that I just told you, by the way, on the front page, the material that is covered. Okay. I'll do a review session the night before, like I normally do, Tuesday evening, just like I did at the other midterms. And there won't be much time after that before we'll all be going remote for the end of the semester. And I'll have more to say about that next week. Okay, that's all I have by way of announcements. Hearing no questions, let's power up the projector here and start talking about chapter 15. I sent out the video lectures for today that was in 2 parts because chapter 15, section 1 is heavy with content. But it turns out that it's all very important content. In chapter 15, we are starting our study of oscillations, things that move in a repetitive way. And that is so important in physics that in a lot of university classes, they'll take oscillations and the related content on waves, and they'll make an entire course on oscillations and waves. We're going to make it a 3-chapter sequence, chapters 15, 16, and 17. Oscillations and waves, very important phenomena. Okay. So that first section of chapter 15 is really heavy on content. I mean, if you don't believe me, look at the learning objectives. Your eyes start to swim. There's so many of them, okay? So what I'm going to try to do is encapsulate some of the most important things. Yet the point of all this is to say, yes, these are all the things we have to do. And in fact, it even spills over onto the next slide. That's how many things we have to understand. In other words, there's a lot because oscillations are so important. So here's what I want to do by way of my summary of the learning objectives. Point out that our standard example that we're studying for chapter 15, our standard example of what's called a simple harmonic oscillator is this picture right here, which depicts a horizontal, frictionless x-axis, a block of mass m, and a spring of spring constant little k. Left end of the spring, one end of the spring is fixed to something immovable, and the other end of the spring is fixed to the block, which is movable. Depending upon the relaxed length of the spring, there will be an equilibrium position where the block would just sit at rest. And we'll always put that at the origin of our x-axis. So x equals 0 is equilibrium. That's where the block would rest and would just sit there if you put it there. Because the spring, if you put the block at the origin, is neither stretched nor compressed. And a spring that isn't stretched or compressed can't exert a spring force. And if there's no spring force on the block, it's not going to move because there is no other horizontal force. Somehow you get this block spring system moving. Otherwise, it's not going to be interesting at all. There's a number of ways to get it moving, as I talked about in the video lectures. You could take the block, pull it out some distance from equilibrium and just let go, or push the spring in some distance from equilibrium and just let go. That'll get it moving. You could leave it at the origin, but reach in and give it a shove, either left or right. That'll get it moving. Or you can push or pull it a certain amount, and then just as you let go, give it a shove. Bottom line is you got to get that thing oscillating back and forth between two extreme points, symmetric about equilibrium. This is the biggest displacement to the right of equilibrium that the oscillating block will exhibit. And this is the biggest displacement to the left of equilibrium, and it's symmetric. And that xm is the maximum x. It's called the amplitude of the motion. And what we did in the video lecture, first part for yesterday, is we said, well, we wrote down Newton's second law and applied it to that and solved Newton's second law for probably the most important thing. What is the x coordinate of the block, like I show right there, at any given time, t? X as a function of t. I want to have a function. You give me any value of t you want, and I'll plug into that function and tell you x, which will tell you where the block is. And that function for x had this form. There was the amplitude factor, x max, and then a repetitive function, the cosine, and the cosine had an argument, and that argument was written that way. Omega times the variable t plus a constant called the phase angle, phi. And I talked about in the video lecture how this function does indeed come from Newton's second law. That's where it comes from. We solved Newton's second law. We wrote Newton's second law for the first time as what's called a differential equation. And we solved that differential equation for x as a function of t. And that's the result. That constant omega, when you study oscillations, and yes, I know we've used that symbol when we studied rotation, didn't we? But now we're talking about oscillations back and forth. So when we have that kind of situation, oscillations, omega is called angular frequency in radians per second. And that constant, omega, is determined by two things, K and M. In fact, omega is the square root of K over M. The square root of the spring constant, how stiff is the spring, that's upstairs, and the mass of the block, how much inertia does the block have, that's downstairs. And where did that come from? Newton's second law. Okay. There's the variable t right there. That means everything else you see here, the x max, the omega, and the phi are all constants that we have to know the values for. And once we know the values for x max, omega, and phi, then you tell me whatever t you want, and I'll plug it in there and tell you the x. How do we find the constants x max and phi? I've already told you how we find the constant omega. We find x max and phi from information that will be given to us in the problem. I'm going to do a Wiley Plus example in just a moment where you'll see what I mean. All right, so one way or another, we've got to figure out that constant, and that constant. And then t is a variable. You tell me t, I'll tell you x. Also, I want to know the velocity of that block at any given time. But it will be a function of time, v of t. And that's just obtained by taking our x solution, x of t, and taking the derivative of it, dx dt. That's how you get velocity. And you got to take the derivative of this with respect to time, and you need the chain rule. And I talked about that. And what you get is negative. You get a factor of omega now out front times x max. And now you have the sign, but with the same argument inside, omega t plus phi. And that's also a helpful formula. I know the numbers, the constants, omega, x max, and phi. So you tell me t, and I can plug into that and tell you v. All right, now this combination right here without the negative sign, angular frequency omega times the amplitude x max, that's the maximum velocity you can have. So your book calls it Vm, Vmax. It's also called the velocity amplitude. But the point is, with this formula, again, you tell me t, I'll plug in, I'll tell you v. So with this formula, I can tell you where the block is, x, and I can tell you how fast and in what direction it's moving, v. But I'd also like to know its acceleration, a, and it's a function of time. This thing will not move with constant acceleration. We can't go anywhere near the constant acceleration equations for all of this chapter. Put them away, lock them up. This thing does not move with constant acceleration. So how do we get that acceleration? Take the time derivative of the velocity function that we just talked about. Do another time derivative now of this, and use the chain rule again. And now you get negative, still there, omega squared x max, and then you're back to a cosine with the same argument, omega t plus phi. And again, now, you tell me t, and this formula, I'll be able to tell you its acceleration. And this combination right here, without the negative sign, omega squared times x max, is the maximum acceleration you can have. A max, the acceleration amplitude. One more thing to note, very useful. It's what your book calls the hallmark equation for simple harmonic motion. It is indeed a very handy way to identify when you have something moving with simple harmonic motion, like this. And that hallmark is, at any given time, the acceleration of the object that's moving with simple harmonic motion will be equal to the negative of the angular frequency squared times the displacement from equilibrium. A at any time is negative omega squared times the x value at that time. In fact, you can see that with my acceleration function right here. Look at the acceleration function I just wrote down. Negative omega squared, and then this part, x max cosine omega t plus phi, is exactly what was the x of t. So you can see right here that that is satisfied. In fact, if you can show that this is true, no matter what the thing is, no matter what it is, then you know the thing moves with simple harmonic motion like that. And later on in the chapter, we'll take things that don't even look remotely like that, not even close to that, and yet have an equation that satisfies the equation has that form. And therefore, we know that thing moves with simple harmonic motion, even though it doesn't even look remotely like a block on a spring. Okay, so those are the key ideas. We have to be able to use everything you see there. That's what this learning objectives boil down to. So let me show you a typical Wiley plus problem, okay? That will require us to use these ideas. I'm gonna have to do my usual thing. I'll show you the problem on the screen, and then I'll have to mute the projector and raise the screen so that I have board space. So here we are. Simple harmonic motion and what are called initial conditions. Here's the scenario. A horizontal simple harmonic oscillator consists of a block of mass m equal to 2 kilograms attached to a spring of spring constant little k equal to 100 Newton per meter. Hey, must be that kind of picture. Block and a spring, horizontal. So I've taken an example that is based on that. Now, here's something else we're told in addition to the m and the omega. When the clock reads t equals 1 second, the position and the velocity of the block are x is negative 0.129 meters and v is negative 3.415 meters per second. So they're telling me x, where is it? And v, how fast and in what direction is it moving at 1 instant. 1 instant only. Happens to be t equals 1 second. Here come the questions. First, what is the amplitude x max of these oscillations, right? What's the number for plus x max and then minus x max? That's called the amplitude. B, what is the phase angle phi of the oscillations? This constant right here. And I'll have to talk about that. That's what this C tip is about. C, what was the position of the block when the clock read 0? Doesn't tell me that. I got to figure that out. And D, what was the velocity of the block when the clock read 0? Okay, I'll remind us of that information as we need it. Now let me get myself some board space. Okay, so example, we used the abbreviation SHM, simple harmonic motion, and initial conditions. Let's start as we begin with part A. We've got to draw a sketch. Yes? I hope I've taught you that much so far this semester. If I'm given a problem with just a bunch of words, I have to draw a sketch. It's going to look something like that, except I want to use the information they tell me about what's going on specifically at t equals 1 second. So we got the wall there. We got the horizontal frictionless x-axis. We take x equals 0 to be equilibrium. And I'll remind you what we're told. At x equals 1 second, t equals 1 second, the x is negative 0.129 meters, negative 0.129 meters. So that's to the left somewhere, right? Let's say right there. I mean, I don't know what the scale is yet because I don't know what the x max is. But there's the block, mass m, compressed spring, spring constant K, this X at t equals 1 second is negative 0.129 meters. That's what I'm told. That's where it is. I'm also told its velocity at this same moment in time. The v is negative 3.415 meters per second. So not only do I know where it is at this time, I know it's moving that way and how fast. Yes? That's v at the time 1 second, negative 3.415 meters per second. I know the spring constant K. Let's write that down over here. 100 Newton per meter. And I know the mass of the block, 2 kilograms. So that's a depiction of what I know. And I know where the block is and how fast and in what direction it's moving at this one moment. And I am to find in part A what's called the amplitude of the motion, X max. First question, how do you think X max, and X max itself is always a positive number, how do you think it's going to compare to 0.129 meters? Is 0.129 meters the amplitude? I'll ask it that way. We have to find the amplitude X max. Is it this number, 0.129 meters? No, I know it isn't, because when it's at 0.129 meters on the left of equilibrium, it's still moving to the left. Yes? So it's still going to go out that way more. I know that. So I know that that X max has to be found. All right, what I'm going to use are the equation for X of t. You can just go right to that. You can go start using it. And the equation for V of t. Okay? So there they are, X of t and V of t. We're going to go straight to them. And let me go ahead and plug in. Let me take advantage of what I know. When t equals 1 second, I know the X and I know the V. Okay? So I'm going to take the X formula and I'm going to plug in for the t 1 second. But the way I'm going to do it is like this. X at time, what I'm going to call T1. T1 is just going to be my shorthand way of writing 1 second. The 1 meaning 1 second. That'll be X max times omega T1 plus phi. Now, X at time T1, that's what that means. That's this, negative 0.129 meters. So I know what the X is at the time 1 second. You see what I'm saying? Yes. Oh, yes, thank you. Certainly need that. That didn't look right at all, did it? Cosine of omega t plus phi. Thank you. Now let's do the velocity. At the same time t1, which is 1 second, that's negative omega x max sine of omega t1 plus phi. That's what I want to write. And these are two equations, so I'm going to number them because I need them both. Equations 1 and 2. In fact, let's go down the line and put check marks and question marks by all the symbols that we either know or don't know. So in equation 1, this represents the value of X at the time of 1 second, but I know what that is, so check mark. X max, the amplitude, the maximum displacement from equilibrium. I don't know that yet, question mark. Angular frequency. I might think I don't know that, but actually I do. We'll talk about that in a second here, but I'm going to put a check by it. T1, that's a specific time moment, 1 second, check mark. Phase angle phi, don't know that, question mark. So how many question marks? 2, two unknowns. Well, that's why one equation isn't enough. Now let's go to equation 2. This is the velocity at time t1 this time. I know what that is. Check mark. Angular frequency omega, check mark. X max, question mark. Omega, check mark. T1, check mark. Phi, question mark. Same two unknowns, X max and phi. So what we actually do is we use equations 1 and 2 to find the two unknowns, X max and the phase angle phi. And we're going to have to talk about that math. But before we do that math, let me show you that, yes, I do know the value of the angular frequency omega. You might have thought that was an unknown because the wording of the problem didn't expressly tell you what the angular frequency of this oscillatory motion is. But remember that very helpful formula when you have a block in a spring system. The angular frequency is the square root of the spring constant over the mass. So that's square root of K, 100 Newton per meter over the mass, 2 kilograms. Note that's the square root of 50. Don't forget to take the square root of it though. But that's what it is, right? The square root of 50. If I give you 3 sig fig approximation, it's 7.07. The units for angular frequency are radians per second. Okay, all right. So now, with these two equations, 1 and 2, how do I do this line I said right here? Use equations 1 and 2 to find X max and phi. Well, we certainly have had situations before where we've had two equations with two unknowns. It is technically algebra problem at that point. The thing that makes this a little more challenging than usual is that one of the unknowns is inside the argument of trig functions. So yes, admittedly, that makes the math a little bit more complicated. Yet it turns out it's actually not too bad. We're just going to have to figure out how to deal with it. I'll tell you one thing I'm going to do right away. I'm going to rewrite equation 2 slightly differently, not much. I'm going to divide both sides by negative omega. So I'll write it down here. Negative V at time t1 over omega equals X max sine of omega t1 plus phi. Let's think of that as a new version of equation 2. Right, just took equation 2, divided both sides by negative omega. If it's helpful, I'll rewrite equation 1 right there with it. Just rewrite it. X of t1 is X max cosine of omega t1 plus phi. My task in part A is to find X max. Let's do that. Let's find X max without first finding phi. Let's try to do that. Turns out it's not hard once you see the trick. Okay, I'm going to take these two with two unknowns, X max and phi. I'm going to solve for X max without first finding the value of phi, which means I got to get rid of phi so that X max is the only unknown. The phi has got to go. How do I do it? The trick is to remember your trig identities. And I'll show you. What I'm going to do is take each equation and I'm going to square both sides. And then I'm going to add them. I'm going to add left side to left side and right side to right side. So the trick is to square both equations and add them. All right, so here, square these, each of these and add them. V squared at time t1 over omega squared plus x squared at time t1, right? The negative sign goes away when you square it. I squared and added the left sides. Now do the same thing on the right sides. Square both sides, square both right sides and add them. Now you'll see why I wanted to get the same stuff in front of the trig functions on the right side, because there's an x max squared on the right side that can be factored. And then I'm left with this, sine squared of omega t1 plus phi plus cosine squared of omega t1 plus phi, close square bracket. Now, this is where I mentioned what is probably the most important trig identity. Okay? One that is beloved by physicists and engineers whenever they can use it, because it really simplifies things. And that trig identity is sine squared of a blob plus cosine squared of a blob equals 1. No matter how complicated the blob is. No matter how complicated. As long as it's the same blob there and there. Okay. Note then that with that trig identity, the phi is gone. And I'm just left with x max squared on the right, which is the thing I wanted. Just take the square root of both sides. Take the positive square root, because the amplitude is always a positive number. So x max equals square root of v squared at time t1 over omega squared plus x squared at time t1. And you've got, once you plug in your numbers, x max. Let's plug in those numbers so that you can see how we do this. And let's do this with care. Let's plug in the numbers exactly as they are. I need v squared at time t1. That's this. Negative 3.415. Negative 3.415 meters per second. Of course, that gets squared, so the negative sign doesn't matter. Still, I wanted to write it to show you the care with which you should do things. Downstairs, I have omega squared, angular frequency squared. There's the formula for the angular frequency. Omega, it's the square root of 50. So omega squared is 50, right? Square root of 50 is omega. So omega squared is 50. And the units would be radians squared per second squared. That's the omega squared. Remember, the unit radian itself is a dimensionless unit. Plus x squared at time t1, all right, plus negative 0.129 meters squared. Be very, very careful with all those squares. It's so easy to make a mistake. Okay, but the squares mean that these negative signs are unimportant in this side, this square root. And when I put that into my calculator, what do I get for x max? Wow, it came out nice and simple. 0.5 meters. 0.5 meters. That means that 0.5 meters out this way and to the right and 0.5 meters to the left are the two extreme points. Larger than 0.129 meters, as I predicted it had to be. Okay? So we've solved for the amplitude x max using two equations. I had two equations and two unknowns. I'm gonna have to get rid of myself some space here. Okay, let me remind you of what part B asked. Part B asked, what is the phase angle, phi, of this motion? That's what that phi is called inside the sine and the cosine there, the phase angle. It basically tells you how much you take a regular cosine or sine and shift it left or right. How are we going to find it? Well, I'm still back to my two equations and two unknowns. And this is now the other unknown, phi. Right? I want the other unknown of the two unknowns from those two equations. Let me show you how to get that without first getting x max, because that's handy. You could have a problem where they don't ask you for x max. then why calculate it? All you got to do is take these equations and get rid of the x max so that you can solve for phi. That's not so bad because the x max is not inside the trig functions, it's multiplying out front. So all I did was I said, let's divide equation 2 by equation 1. That means divide left side by left side and right side by right side. So when I do that on the left, I have v of t1 over x of t1. That's what I have on the left. On the right, when I divide this side by this side, notice the x max symbols cancel. And I've got a negative omega, and then I've got sine blob over cosine blob. Well, that's just tangent blob. So now there we are. With the only unknown being phi. That's the only unknown. It's tricky because the phi is inside a trig function. So we got to get to that phi, right? So let me divide both sides by omega, negative omega, in fact. Looks like that. Okay. Do you have a question?
Yeah. So like when we're doing these problems, how do we know when looking at parallel, do we have like kind of like put our problem aside? Oh, this is something we need to divide by the other, or
it's not so much that you just have to say, well, I've got 2 equations and 2 unknowns. I've got to bring all my algebra 1 and algebra 2 and trig that I've learned in high school to bear to solving these 2 equations. Okay? And it isn't that, and I'm not claiming that this is the only way to solve for phi. There is more than one way mathematically to do it with these 2 equations. I'm showing you the way to get phi without first getting x max. Because, as I said, in some problems, you may not be asked to get x max. Then why go through the extra step of getting it? So bottom line is, you just got to say, okay, all that math I learned in high school, when the teacher was pounding that into my head, solving equations, working with trig functions, I need to bring all that to bear. Okay? All right. Now, how do I get to the phi? Well, a tangent of it's inside there, right? You know how to get rid of a trig function? You take its inverse. You take the inverse of both sides, inverse tangent. So on the left, I'll have inverse tangent of negative VT1 over omega XT1. And on the right, once I take the inverse tangent, I'll just have the argument inside the tan, omega T1 plus phi. Let's go ahead, just to make it look a little bit less daunting. Let's get this number on the left side, because this is all stuff I know. But now let's do this exactly what it says. There's a negative sign there. Then I take v at time t1, negative 3.415 meters per second. See, I told you have to be careful. Over omega, omega, not omega squared, 7.07 radians per second. And x at time t1, negative, wow, 0.129 meters. Well, you really got to be alert. Look at all those negatives. You got to put them all in. And then over here, you still have omega T1 plus phi. Now, let's see. There's a meter here and a meter here. There's a per second here and a per second here. All those are canceling. Radian is a dimensionless unit, so it doesn't actually count. So there's actually no units at all inside there. And all you're doing is taking the inverse tangent of whatever that is on your calculator, and that is negative 3.74. And that must equal omega T1 plus phi. Okay, everybody see what I've done so far? This is the kind of math we have to do when we study oscillators. Now, this one shouldn't be too daunting. Just go to your calculator. Calc, short for calculator. I recommend in chapter 15, you put your calculator in radian mode and keep it there, because we're going to work in radian mode. So you put your calculator in radian mode, ask it to take the inverse tangent of negative 3.74. And it will give you, if I give you 3 sig figs, negative 1.31, and it'll be radians if you've got your calculator in radian mode. Okay? Then there's really just one more step. Remember, we're solving for the phase angle, phi. Here. So just do some rearranging. Phi is what I got from the inverse tangent on my calculator, negative 1.31 radians minus omega, 7.07 radians per second times T1, 1 second. Of course, the per second and the second cancel, and that's in radians, and that's in radians. So phi is in radians. The phase angle in radians. Well, it's clearly going to be negative. I'll tell you what you get. You get negative 8.38 radians. And it seems like we have the phase angle. Okay. Note, by the way, you can take any phase angle for any trig function, and you can add or subtract, if it's convenient, an integer multiple of 2 pi. And it will not affect the outcome, the output of the sine, cosine, or tangent, because those functions are said to be 2 pi periodic. So sometimes you'll see people add, for example, 2 pi to that to get it within a certain range that they want. You're allowed to do that. You're allowed to add or subtract 2 pi or 4 pi or 6 pi or 8 pi, and it won't affect the outcome of any trig function. Very handy thing to remember. But that's not the subtle thing. The subtle thing is we've actually got a lurking problem here, a situation that is a problem. And that's what I need to show you. So I need to come back to the screen and show you the next slide and talk about what's wrong with our phase angle. Turns out that's not correct. Let me explain why. It's all because, and there's no way to avoid this, we had to take an inverse trig function, in this case, inverse tangent. And whenever you take an inverse trig function on your calculator, you need to be aware of kind of a snake lurking in the grass. Okay, here we go. To show you what I'm talking about, I'm going to plot the function tan. I'm going to plot tan x versus x, where x is just a variable. So x in radians and tan x vertically. And I've plotted it over, you always want to plot over a domain of at least 2 pi radians, because the function's 2 pi periodic. So I plotted for x between negative pi and pi. That's tan x, for x between negative pi and pi. Don't be distracted by these vertical asymptotes. They're not anything but a guide to the eye. Okay? That's tan x, goes up and diverges up there, and then comes from down here and goes through the origin, and then goes up that way and so forth. That's tan x. What are you doing when you go to your calculator and say, hey, calculator, tell me the inverse tangent of negative 3.74? You're saying, tell me the angle whose tangent is negative 3.74. Let's do that graphically with this graph. Let's find negative 3.74 on the tangent axis. Tangent. Negative 1, negative 2, negative 3, negative 4. Negative 3.74 is roughly about there. You want the x value whose tan x is negative 3.74. So start there and go horizontally, left or right. I'm going to go left until you hit the curve, the tangent curve, and then go up to the x-axis. All right, I get right about there, which is clearly a little bit more than negative 1.2. Well, my calculator gave me negative 1.31 radians. That seems right, is my point. That's what your calculator is giving you. It's going boom, boom, bop. There's the answer right there. That's what your calculator is doing. Well, it's not looking at a graph, it's using something called a power series, but that's the way that we'll think about it with this graph. But here's my point. On this 2 pi domain, 2 pi radian domain, there's another possible x, isn't there? Whose tangent is negative 3.74. Namely, get to negative 3.74. Now let's go to the right until we hit the curve. Don't worry about the asymptote. There. And then go up. Up there. That's another x whose tangent is negative 3.74. Perfectly possible. Mathematically. Why didn't your calculator give you that other possibility? It's not programmed to. It's only programmed to tell you the x within this range right here, between negative pi over 2 and pi over 2. And it is programmed to ignore any other possibilities. But the other possibility, it turns out, which was over here, remember, a little less than 2, is the answer I had over here, negative 1.31 plus pi. Why plus pi? Because these two asymptotes are exactly pi radians apart. So another possibility on this function is x is negative 1.31 radians plus pi, which is 1.83, which is sure enough about what I'm seeing right there. See what I'm saying? So 1.83 radians is another possible value for the number that was put into that slot. Okay? So we have to recalculate the phase angle phi using this other possible answer for that inverse tangent value, 1.83. So I did that right here. I just redid that phi calculation, but now I'm using 1.83 radians in the first slot, minus omega t, minus omega t. 1 second. I get negative 5.24 radians. So now my question is, which is it? Which is the correct value for the phase angle? Negative 8.38 radians or negative 5.24? Mathematically, it could be either. But it turns out physically, only one of those two is correct. Only one of the two is correct. How do we figure that out? Here we go. So which phase angle do we use? Negative 8.38 radians or negative 5.24 radians? Answer. Use the phase angle, whichever one, gives the correct values of x and v at t equals 1 second, because I was told what those were. For example, we have to have the x value at t equals 1 second be negative 0.129 meters, because that's what I was told. I claim that of those two phase angles I've got written on the board, only one of them gets this right. Let's check it. Let's actually plug in for x of time 1. Here's x max. Remember, we found that already, 0.5 meters. Cosine of omega t, that's all the same. And then I just put in the two possible answers for phi. Negative 8.38 radians and negative 5.24 radians. Did that carefully in my calculator with my calculator in radian mode. And for the first answer, I got x to be positive 0.129 meters. Watch it, positive. No, that's not what the x1 was, right? The second answer is correct. It gives me x at time 1 of negative 0.129 meters. So now I know which of these two is the correct phase angle. It's the one I've written in green. Stop with the red one. It's the green one. Phi negative 5.24 is the correct answer. Note, not the one you would have gotten from your calculator. Got to watch out for that. That's the snake in the grass, because the calculator is only programmed to give you inverse tangent values within this domain. But we needed the one that was out here. You can check for yourself, by the way, that phase angle, negative 5.24 radians, also gives you the correct value for v at time 1 second. All right, the last parts now fall out very quickly. Part C. What is, or was, if you like, the X value at time 0? Just take the X equation. By the way, we now know the full X equation. X of t equals X max, 0.5 meters, cosine of omega, 7.07 radians per second times t plus phi minus 5.24 radians. And all you got to do is tell me the t, and I'll plug it in and tell you the x. And I'm told in part C to plug in t equals 0. So x of 0 is 0.5 meters cosine of negative 5.24 radians. I just plugged in t equals 0. And you can do that in your calculator. Be very careful. Make sure it's in radian mode. And I get for the x0 positive, yes, positive, 0.251 meters. It's on the right side of the origin at this moment. And then it asks me lastly, what is the velocity at time 0? For this, you need the velocity formula for any time t. That's negative omega x max sine of omega t plus phi. But plug in t equals 0. V of 0 is negative omega x max sine of phi. And now plug in numbers. Omega 7.07 radians per second, x max 0.5 meters, phi negative 5.24 radians. Calculator in radian mode, you get negative 3.05 meters per second. Negative. Well, let's draw one more picture. Let's show what it's doing at time 0. There's equilibrium. It's located to the right. Here's x0, okay? A positive x, but it's moving to the left, v0, because the v initial is negative, with the spring, of course, still there. There's the t equals 0 picture. Note then what happens between t equals 0 and t equals 1. Starts there, but t equals 1, it's somewhere over here going to the left. If you want a little more practice, calculate what the period is. You can get it from the angular frequency, omega. You get 0.889 seconds for the period, which is less than 1 second. So between t equals 0 and t equals 1, it comes over here to negative x max, comes back over here to positive x max, and back to where it started. That's 1 period, and then to about there. And that's where you are at t equals 1 second. Bottom line, we have to be able to calculate everything there is to know about a block and spring. Everything. That's how important it is. Okay, tomorrow's class will be online, so the videos will be coming, and then we'll be back here on Friday. All right? No quiz on Friday. Good day. Have a good day.